Hello there, I'm Niklas. I'm going to present Edge Replication Strategies for Wide Area Distributed Processing. This is work that I did in cooperation with Matthias Rost, Georgios Smaragdakis and Anja Feldmann. It's a cooperation between SAP, TU Berlin and MPI. Let's take a larger look at edge-based data processing. So on the left, you have many new use cases that generate lots and lots of data. This data is moved to the edge where it's locally processed and temporarily stored before parts of it are moved to the data center for heavy processing and content distribution. The challenge is that in the middle of the two, you have the internet, a shared best effort infrastructure, which means that it has limited bandwidth and you have to pay for transfers. So how do we reduce transfer data volume? Let's zoom in on a single setting. Let's say you have some use case that produces data and you have an application in a data center that attempts to access this data. Now there are two ways you can access the data. Either you forward the query and retrieve a result, or you replicate the raw data and then process the data in the data center. The cost is for the former case that you pay per query results. So it's cumulative. On the other hand, for the replication, it's a high one-time cost. So the former is good if you have few small non-overlapping results, and the later is better if you have many large overlapping results. The challenge here is that you don't know what will happen in the future. So you will know the demand in the past, but you don't know how the demand will look in the future. Here is where our replication strategies come in. This is a strategy that determines when data is replicated given a record of its past accesses. And the naive strategies are to replicate immediately or replicate never. The optimal offline strategy is to replicate immediately if the future demand is larger than the replication cost. Now the former is data dependent and the latter requires knowledge of the future. Both are not good choices. We don't have the knowledge of the future and we would rather have something that's not data dependent. So how can we do better? Well, let's first look into how data is organized. Here we assume a use case where data is immutable. This could be the case because machine logs or click logs or other kinds of logs are stored. And then the data is partitioned according to some logical criterion, which could be by machine, by location or user group. Each partition is accessible for a time window. After this time window, it's removed or archived due to storage reasons. For this use case, we have found a dataset, which is a trace of an ERP database of a global 2000 company. This trace has records access at a row level, and we define here a partition to be 10,000 rows. The trace is about 2 days long, and so we define the time window to be 1 day. The trace looks as follows. You have on the y-axis the partition or partition ID, and on the x-axis the time in the individual days. The color indicates how often this data was accessed in a time interval. And please note that the data is the color scheme is logarithmically scaled, so the difference between the individual transfers are quite high. Now if we take a look at our naive strategies, the former replicate nothing has a cumulative cost, so the sum of query result sizes sent over a time window, and the latter has a replication cost, which is basically partition size times a replication cost factor, which could be influenced by compression or overhead. If we evaluate this on our dataset, here we have on the y-axis the transfer volume in rows and on the x-axis the replication cost factor. And the three lines represent the three strategies. So you see that when replication is cheap, it makes sense to replicate everything, and this is close to the optimum. But when replication is costly, you're better off replicating nothing. And in between the optimal offline and the two strategies, there's a huge gap where performance could be improved. And if you compare the best of those two naive strategies to the optimal offline, we see that for most cases, we have a potential reduction of more than 50%. So that means that optimally, you could halve the transfer cost that you're sending. Well, let's look at advanced strategies to achieve anything in this direction. So we have 3 types of replication strategies. Those are the that we introduce. Those are the competitive replication strategies, heuristical replication strategies, and hybrid. Competitive means you have a guaranteed worst case performance. Heuristical means we exploit the access traces, and hybrid is a combination of the above. With competitive strategy mean a strategy that has a bounded worst case performance in comparison to the optimal offline strategy. This is, for example, skew rental strategy, which we use in our system. So this is an algorithm that was devised by Cullen et al. And uses a threshold to decide replication. If past transfer costs, so the transfers cost up to this point, have been higher than the replication cost, then you replicate. This is a too competitive algorithm that is provably the best worst case bound. So why would you need any more than that? Well, if we look at the data set, we can extract certain insights. First, we see similar activity in similar regions. Second, we see repeating activity or repeating patterns in the 2 days. So this gives us hope that popularity of a partition, which means that a partition will be heavily accessed later on, might depend on a location. So it's partition ID. And there might also be patterns in the data that indicate where a lot of transfers are still coming. If we take the full time window and look at the transfer cost during the full time window, then we see a skewed relationship between all partitions. So here we have an ECDF that shows all partitions depending on their full transfer cost for the full time window. And what you notice is that 50% of all partitions have fewer than 1,000 accesses, and smaller than 1% of all partitions have more than 100,000 accesses. This indicates that this is a skewed distribution, and that accessed partitions are more likely to be accessed in the future than not. This also indicates that you should replicate earlier than the skew rental does. We have developed 3 heuristical strategies. The last partition strategy basically looks at the same partition in the last time window to decide whether it should replicate in this time window. The last threshold computes the best threshold over the past partitions in the past time window, and then applies this threshold to the current time window, which is similar to the skew rental, only that you estimate the threshold from the trace that you've seen. Finally, we have a machine learning classifier, off-the-shelf random forest, that classifies patterns regarding whether the corresponding partition is exceeding or not exceeding replication cost. And then we replicate a partition if it matches those patterns. So we combined the competitive and the ML strategy, so skew rental and classifier, in a way that we say if either of them want to replicate, we replicate. Here we configure the ML to be very conservative. So it will only replicate if it's very sure. The goal is, as indicated earlier, to replicate earlier than the pure skew rental, and so save more transfer cost early on. Because the skew rental will always wait till you have seen partition transfer costs that are equal to the replication cost. We have discussed 3 types of replication strategies, competitive, heuristic, and hybrid, with 5 different strategies. And now we compare those to the naive baseline, which is the minimum of replication all partitions and replicating nothing, and the optimal offline. And we use that by utilizing the second day of our trace. The transfer cost reduction that we show here is compared to the naive baseline. You see that on a y-axis, and a replication cost factor on the x-axis. So left here means that replication is cheap, and right means replication is costly. Factor above 1 means it's worse than having than a baseline, and a factor below 1 means that it's better than a baseline. So let's first look at the skew rental strategy. This strategy performs well in comparison to the optimal offline and definitely outperforms the baseline for most cases, almost all cases. There's still a gap between the skew rental and optimal offline, but it's getting close. If we look at heuristics, we observe that the last partition strategy performs rather badly. So the partition of the last time window does not indicate whether the partition of the current time window should be replicated. The last threshold, in contrast, performs close to the skew rental for most cases. So that indicates that the skew rental is actually a very good threshold. If you look at ML, machine learning or the machine learning classifier outperforms the baseline, but does not perform as good as the skew rental. The hybrid does perform close to the skew rental and even outperforms the skew rental in a few cases, particularly on the left here, close to 0.1. So how did that happen? Well, let's zoom in onto the hybrid strategy. Here we see the three strategy, classifier, skew rental, and hybrid, for three different types of metrics: precision, recall, and mean time of replication. And you can immediately notice that the recall for skew rental is 1.0, which is due to the fact that skew rental will replicate when the replication cost is exceeded. And the recall of the classifier is far worse, but it's replicating sooner. And if you compare the mean time of replication of the skew rental and hybrid, you can see that the skew rental replicates a bit later than the hybrid. So we see some gain here, and the precision is the same. So this can explain the gain that we have seen before. To conclude, we have introduced several replication strategies, and the skew rental strategy reduces the transfers by 22% on average and 50% for the best case. Here we describe the results for both traces. We've just shown one trace here, but there's another trace in the paper. And the hybrid strategies improve the performance by 25% on average and 51% in the best case. Now, we have used an off-the-shelf algorithm, and we have for machine learning, and we have only used very little data. So there's a good chance that a better machine learning algorithm would perform far better. And this is ongoing work where we look at what other algorithms could perform better. We also want to include in the future other cost factors such as storage, etc. Now, if you're interested in the performance of this system on your data, please contact us. The mail is here, and thank you for your attention.